Thorium is a kind of miraculous element. Thorium found in nature isn't fissile. The atom's nucleus won't split when it absorbs a neutron. Yet if you put a chunk of thorium in a special nuclear reactor, after a while most of the thorium will be gone. A whole bunch of energy will have been generated. You will be left with typical byproducts of fission. It is as if thorium is fissile, even though it is not. This is the genius of thorium breeder reactors. The standard oversimplified picture of a fission reactor is a uranium nucleus splitting apart, or fissioning. It releases heat energy and 2 or 3 neutrons. Those neutrons go on to be captured by more uranium nuclei and cause them to fission. This releases more heat energy and more neutrons, and so on. The heat is used to generate electricity. The neutrons maintain the fission chain reaction. However, the actual story is more complicated. When a nucleus splits, there are 4 things that can happen to the neutrons it emits. 1, they can be captured by a fissile atom like uranium-235. This causes it to fission and release more neutrons. This part has to happen on average at least once per fission to sustain the chain reaction. 2, neutrons can be captured by the nuclei of other atoms in the reactor without causing fission. This could be the metal case, the moderator, the control rods, or whatever. 3, neutrons can escape and leave the reactor entirely. 4, a neutron can be captured by an atom that is not fissile and transmuted into an atom that is fissile. Remember, these are atomic nuclei we are dealing with. Absorption of a neutron will turn uranium-238 into uranium-239. The number is just the total number of protons and neutrons. Uranium can then radioactively decay into neptunium-239. That can then decay into plutonium-239, which is fissile. If the capture of a neutron transforms a non-fissile element into a fissile one, it is called a fertile capture. Fertile capture is what makes thorium useful. In fact, even in a normal uranium reactor, fertile capture accounts for over 1/3 of the energy generated. A normal nuclear reactor uses uranium-235, which is fissile. But naturally occurring uranium ore contains only 0.7% uranium-235. Almost all the rest is uranium-238, which is essentially non-fissile but is fertile. Even when using fuels with enriched levels of uranium-235 undergoing fission, there is so much non-fissile U-238 around that some chain reaction neutrons instead transform U-238 into plutonium-239. That plutonium can then fission. But U-235 does not make enough neutrons. U-238 does not turn into plutonium easily enough. So you cannot both sustain a fission chain reaction and continue to transform new fissile fuel. At the end, you are left with a big chunk of unfissioned, but still radioactive uranium-238 waste. There is a different kind of reactor called a fast breeder reactor. It uses plutonium as the primary fissile fuel and uranium-238 as a fertile secondary source. This combination can both sustain the fission chain reaction and transform new fuel in a self-sustaining way. But fast breeder reactors are less researched. They are more expensive. They are harder to run effectively for now. This is where thorium comes in. The same route used in the transformation of uranium-238 to plutonium-239 can be replicated down here. Start instead with thorium-232. By adding a neutron, we get thorium-233. That decays to protactinium-233. That decays to uranium-233, which is fissile and can be used to generate energy. So if you load your reactor with thorium-232, which is not fissile, and throw in some starter fissile fuel, then for each fission reaction, the number of new fissile atoms created is more than 1 on average. The number of new atoms split is more than 1 on average. Those atoms give you more neutrons. So the transformation of thorium and the fission of uranium can keep going and going until in principle all of the thorium is gone. Crucially, thorium transformation can happen in a reactor that does not have the same challenges as a fast breeder reactor. It gets rid of most of the long-lived radioactive waste. Thorium is more abundant than uranium. It does not need the expensive refining process to concentrate fissile uranium-235. So you can see why people get excited about thorium. There are of course challenges and downsides to making thorium reactors. That is why we do not have commercial energy generation from thorium yet. But that is fertile material for another time. Making commercial power from thorium may soon be possible thanks to organizations such as Copenhagen Atomics. Copenhagen Atomics is building compact modular thorium reactors to produce cheap energy. Unlike traditional nuclear power stations, which are giant infrastructure projects, Copenhagen Atomics is designing a self-contained reactor unit that can fit inside a shipping container. These reactors can also use plutonium waste from classic nuclear reactors as fuel. They extract 10 times more energy out of spent nuclear fuel than the initial reactor did in the first place. In doing so, they convert long-lived radioactive waste into short-lived radioactive waste. In theory, these reactors could run anything from grids to ships to moon bases.